Hello, my name is Wachtmeister, and in this video I want to present the results of my master thesis, Model-Driven Systems Engineering for Virtual Product Design. If we want to develop a system in a traditional way, we could think about its environment and its intended functionality, maybe write down these results in any form of documentation, and then directly build a hardware prototype. We can use this hardware prototype in its final environment to check whether the system meets the requirements or not. If the requirements are indeed fulfilled, we're happy and we can use the system for its intended purpose. If the system does not fulfill our requirements, we have to repeat the process until we created a system which meets all our requirements. Even though this simple method worked well for hundreds of years, complex systems such as aircrafts, cars, or smart manufacturing systems require a more advanced method for a successful system development within its cost constraints. For that reason, systems engineering aims to support a system engineer in all stages of the system development process. The system development steps usually include activities to handle system requirements, design, analysis, and verification activities. In addition to these activities, also validation activities could be performed. For a long time, systems engineering solely focused on creating documents. Model-based systems engineering does not focus on creating documentation only, but focuses on creating models that support requirements, design, analysis, and verification activities. In the shown image on the left, we can see that based on a set of requirements shown in a SystemL requirement diagram, we could create a SystemL block definition diagram from which other models, such as a technical drawing or a CAD model, can be created. To analyze the system, we could also use mathematical formulas, SystemL parametric diagrams, or instances shown in SystemL block diagrams, which have the advantage that we can use them to create analysis results and simulations. To visualize the difference between a model-based systems engineering approach and a model-driven system engineering approach, we start by taking a closer look at the following model-based systems engineering definition. To get a more general overview about model-based systems engineering, we take a closer look at the definition from the International Council of Systems Engineering called INCOSE. According to the INCOSE, model-based systems engineering is the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities. Although this definition has the advantage that it clarifies that models and modeling should be used in all stages of the system development process, it has the disadvantage that it does not enforce any use of models in a constructive way. This conceptual uncertainty led to the problem that systems engineers only used models as an additional system description, which did not provide any further information for the following development stages. To improve the value of models in the systems development process, it is therefore a good idea to increase the value of the system models in the process itself. For that reason, model-driven systems engineering describes a model-based systems engineering methodology in which system models are the key artifacts of the engineering process. For that reason, system models created in a model-driven systems engineering approach must be sufficient to generate other descriptions that address systems, requirements, design, analysis, verification, and validation activities. By generating other descriptions, we mean in this context a transformation or refinement of models in order to address other aspects and views of the systems engineering process. To demonstrate the capabilities of model-driven systems engineering, I began my thesis with modeling the following case study in SystemL. In this case study, I created an abstract SystemL model of the IceCAD demonstrator that was originally developed by the Werkzeugmaschinenlabor at the RWTH-Aachen University. The IceCAD demonstrator provides functionality for storing, cleaning, priming, and quality assurance of car windows. To achieve this aim, it consists of 5 cells for storing, handling, cleaning, priming, and quality assurance of these car windows. In the SystemL block definition diagram shown on the right, we see that a block called IceCAD demonstrator consists of a cleaner cell, which is our system of interest, a storage block, a quality assurance block, a primer block, a handling block, and additionally a physical environment block. While this SystemL block definition diagram is suitable to describe an abstract view on the system, it is not inherently capable of describing its actual design. For that reason, I developed a process in my master thesis that embeds system descriptions in SystemL into a virtual product development environment. This process, which is shown in the left, starts with a SystemL modeling activity, which aims to create SystemL models as the one shown for the IceCAD demonstrator. Based on this abstract system model, the CAD modeling activity aims to create CAD models which describe the geometry of all hardware elements. Optionally, it is possible to store the CAD model in a digital mockup unit, which can be used in a computer-aided engineering analysis process. The computer-aided engineering analysis activity uses the CAD model to simulate the system behavior in order to verify the system requirements. If the system design fulfills all requirements, the computer-aided manufacturing activity aims to provide methods to actually manufacture the system hardware. In virtual product development, so-called CAX process chains support the connection of computer-aided methods. Commonly used process chains are the CAD-CAE process chain, which analyzes a system design using computer-aided engineering modules, a CAD-DMU process chain, which creates digital mockup units based on a computer-aided design model, and the CAD-CAM process chain, which actually manufactures a system based on its computer-aided design model. While most of these process chains were already developed in virtual product development, a missing link is the SystemL CAD process chain. To establish this missing connection, in my master thesis I developed a SystemL Profile which allows to connect CAD models with SystemL descriptions. A SystemL Profile allows to extend UML-related languages. For example, SystemL itself is only a profile extension of the unified modeling language. To connect abstract system descriptions in SystemL block definition diagrams with CAD models, we use the following two concepts. First, we describe blocks as CAD elements to denote that this block should be modeled in a CAD model. And second, we mark value properties as CAD parameters to denote that these parameters should describe our CAD model. To actually implement a SystemL CAD process chain, I developed a MetricDraw plugin which allows to import and export parameters of CAD elements. Before we can use the MetricDraw plugin, we have to install it. Therefore, I would like to explain how to install the plugin in the following. To install a MetricDraw plugin, we simply have to copy our plugin into the plugin directory of the MetricDraw installation directory. After we successfully install the plugin, we can use it in MetricDraw after the next startup. To demonstrate the capabilities of the plugin, I want to present the creation of a Venturi nozzle design in the following. The Venturi nozzle I designed in this example is derived from a general Venturi nozzle design, which has an inlet parameter D and a compression parameter d. In addition to these parameters, the concrete Venturi nozzle design in this example has more parameters which can be used to derive a concrete Venturi nozzle instance by specifying the parameters of the Venturi nozzle design. Using the CAD plugin, we can now export the parameters by first setting the output directory and then clicking on Export Parameters. After exporting the parameters to an Excel sheet, we can go back to the Venturi nozzle design and open the Autodesk Inventor file and see that based on the parameters we generated, a concrete Venturi nozzle design was generated. Vice versa, we can modify a generated Excel sheet, save the changes, close the Excel sheet, and then use the CAD plugin to import the parameters we previously modified. The value changed and the import was successful.